Okay, so we got cut off on that other one. Actually, I reached my recording limit, so and I've since shrunk this one, so I hope this is still helpful. Let's finish where we were. Remember what we were doing. We were taking samples of size 10 from this uniform distribution, and there's an example. There's one sample of size 10, and there's the mean, right? Let's do it again. Actually, I'm just going to hit 5, and we're going to do it 5 times. So while I talk, so notice there's a sample of size 10 coming down. We get samples from across the board, and then we find the average, and that drops down on the bottom graph, right? Remember, this is a uniform distribution, so we're just as likely to get these values as these values. This is like rolling a 50-sided die, right? That's what a dice is, uniformly distributed. You know, you're going to get all values across equally, and you see that. So you get some high, some low. But look, you got some low, some high, but look, the highs and the lows cancel out and you still end up with a mean that plops right down here in the middle. Okay, so again, we're interested in the distribution of sample means, not of the distribution of individual data points from the population. Okay, so we're gonna do this a couple more times, and there's a reason I was showing you this. Remember, our population starts off as a uniform distribution. But we're interested in what's the distribution of the sample means. What's the sampling distribution of sample means? I hate saying so many words, but that's what we're interested in. So there we go. We've done this 12 times, and so there are 12 means right there. I'm going to do 1,000 more, right? Bam. And look at this. So we did this 1,000 more times, but look at what's happening. This distribution of sample means, here's 1,000 more. This is getting more and more, looks more and more like a normal curve. Okay, and look, 1,000 more, 1,000 more, 1,000 more. There's the distribution. So look, the population had a uniform distribution, but the sampling distribution of sample means is normal, which means we can predict perfectly, almost perfect, theoretically perfectly, what our sample means should be, which is great because that's what we use. We use sample means in statistics. Okay, let me do this one more time, but let's not use a normal distribution. Let's see what else we got here. We've got, what about a skewed distribution? Do we have a skewed? Frame. Yeah, so let's do one that's right skewed. And yeah, so here we go. Look at this. There it is. Look, this is the distribution of the population. So when we start randomly selecting things, let's do 10 again. When we start randomly selecting things, we would expect to get more values in this end than here. All right, so there it is. There's our first time. Most of our values are down here in this big fat tail, or the fat part of the graph, right? We've got a few there. So we'll do it 5 more times. So we get a sample of size 10, and look what happens. Bam, there's the mean. Okay, so again, we're getting most of our values from this area of the population. Now that one had some big values, but look, the mean still becomes right in there. It's really, the averages, sample averages behave predictably. That's what we're learning here. Even when the population itself that we take them from is not predictable or not super nice, not normal, sampling distribution of sample means becomes very predictable. Again, our means are clustering right here, right? So you just notice that even when we get values that are way high, way low, bam, the means are right there, okay? So as soon as this goes, when it finishes its little cycle, we will do this 1,000 times. And I want you to see something that happens again. Oh, let's do it 1,000 times. There it is. Look at that. There's 1,000 more. There's 1,000 more. There's 1,000 more. 1,000 more. 1,000 more. 1,000 more. Right? Bam. And so look what happens. Again, I get normal. I get that the sample means are normally distributed. Right? So now when I start asking questions about the likelihood of getting a particular mean from a study, I can assume I'm always working with a normal curve because the sampling distribution of sample means are normal. Regardless of what the population is, that's what we see here. when the population was skewed, when it was uniform, or even when it was normal, the sampling distribution of sample means becomes normal. We can do this. This is kind of fun. We'll finish on this one. So I can do a custom one. Watch what I can do here. I think this is the way this works. I can draw it in, right? So bam, there's the distribution of our population, right? I don't even know what you call that, right? Multimodal, right? But you would expect to get values in here, in here, in here, in here, and here, right? So here we go. Let's take a sample of size. Oops, we need reset. We need to move this to sample of size 10. I'm going to try that again. Sample of size 10. And let's throw in 5. And so there you go. Now, boom, there it is. There's our first mean from sample of size 10. Okay, we're going to do that again. Here's our next mean from a sample of size 10. Look, it plops right in the middle. So even though these things coming from this population are, kind of clustered, you're going to get a bunch in here, 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 and here. Look at the means. They are right there. Okay. Okay. So let's do it 1,000 times. Look at that. We start getting a normal distribution for the sample means. Another 1,000 times. Still normal, more normal. So even though the population is wacky, right? The sampling distribution of sample means is normal, okay? Is normal. Okay, so that just gives us the ability to assume that whenever we're dealing with sample means, we can assume normality. Whenever we're asking questions about sample means, we can ask questions about, or we can assume normality. Okay, let's go back to a uniform population right here. And I want to just show you one last thing, because what we notice, no, that's not, I don't want uniform. I want bell curved, of course. Normal, okay, bring that back in. Okay, so there it is, right? Now, let's work with a sample of size sample of size 10, because that's what we're playing with. And I'm just going to pop down 1,000 samples. Boom, normal, 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 normal. And look, so our sampling distribution is normal. Okay, now we need to notice a couple things about it. Number one, look at where the center of this sampling distribution is. You can read it off right there, 100.08. Where's the center of the population? 100. So one of the things we're going to learn is when we're dealing with means, when we're dealing with sampling distributions of sample means, the mean of the means, that's what it is. This little yellow line is the mean, the average of the averages, right, is going to equal the average of the population. Okay, so that's a little thing to have in our toolkit. Now, what about the standard deviation? The standard deviation is, of course, the width, right? How wide is this curve? Well, clearly this curve, which is the distribution of means, is narrower than this curve, okay? So we're not going to be able to say that the standard deviation of the sample means is the same as the standard deviation of the population. In fact, it's not. The standard deviation of the population is 15. You can see that up here. That's what we said before. And then this is 15. This is not 15, right? 4. Now notice it's smaller, which is good, because that tells us that the variation of the means is less. The curve is narrower. Okay, so that means the means are clustered more. We don't get means bouncing around all the time. They're going to be more clustered in the center. Okay. So in fact, we have a nice, neat formula. The standard deviation, and don't worry, I'll put this in writing so you can see it. But the standard deviation of the sample means, is this standard deviation divided by the square root of the sample size. So this standard deviation is this standard deviation. So 15 divided by square root of 10. Okay. So the reason I say that is because this is what this means. If the sample size is larger, then you can expect you're dividing by square root of a larger number. And so you can expect the standard deviation of the sampling distribution to be smaller. The larger the sample size, the narrower this bell curve is. Okay, let me just show you this. Let me prove it to you. So let's go to a sample of size. Well, let me remind you. Here's a sample of size 10. We'll do that 4,000 or 5,000 times, right? 9,000 times. So see how wide that curve is, right? With a standard deviation of about 4.7. That's with a sample of size 10. If I reset this and do a sample of size 2, so smaller, what's going to happen is I'm going to get more variability. My standard deviations or my means are going to spread out more. Now look, see how wide it is now? Boom. So the smaller the sample size, the wider, the greater the variance in your sample means, the wider the bell curve representing the sampling distribution is going to be. Okay. So we kind of expect that. Basically, that's saying if we take larger sample sizes, then we can expect the mean, the statistics we calculate from the mean, to be more clustered around the mean of the population. Okay, we don't expect lots of means way out here on the edges. Okay. Now, interestingly enough, if I take samples of size 1, I'm going to get a bell curve that looks a heck of a lot like the original population, right? Even look at the standard deviation is 15, the mean is 100. We knew the mean would line up because the mean always lines up, but the standard deviation is the same, right? So if you're taking samples of size 1, then you're just dealing with the population. But if we take samples of size, say 100, we should expect a very narrow bell curve down here on the bottom. In other words, our sample means are not going to vary very much. Look at that, right? So this is why it's great to take samples of size 100, because you can expect your sample to be pretty dang close to the mean of the population, right? Okay, so that's a little bit about sampling distributions. Now, all of this discussion that we've had has been with the statistic of the mean, right? But a sampling distribution, we started this example by saying, okay, today we go out and sample 10 people and find their average IQ. Tomorrow we sample 10 more people and find their average IQ. And then the next day, 10 more people and find their average, right? So we have a bunch of averages. Those are our statistics. Well, I could do this with any statistic. I could go to 10 people, find their IQ, and find their sample standard deviation. Go to 10 people tomorrow, survey them, find their sample standard deviation. Go to 10 people, 10 different people the next day, find their sample standard deviation, and I can get a distribution of sample standard deviations, a sampling distribution of sample standard deviations. We can do this with any statistic. We're going to only look at 3. We're going to look at the mean and proportion, probably mostly just the mean and proportions, right? So anyway, that gives you an idea of what we're talking about, and I hope that helps.